All right, hello, everybody. Hello, welcome back to Math 126. How's everybody doing today? Hopefully, everybody's doing fantastic. All right, we're here to do some work today. Hopefully, everybody had a wonderful weekend. I hope you did. Um, yeah, so we're here, we're back. Gonna be doing another couple sections here today for sure. Get that stuff out of the way, get it done, and hopefully we'll then end it off there. Simple as that. Hey Lee Wen, how are you? Good to see you again today. Hopefully you're doing well. Emma, hello. Emma, hey, I saw you on Discord, tried to talk with you, and then you logged off. I wasn't sure what was going on. Is everything okay? I was like, because you said you had some questions, so I was like trying to help, and then wasn't sure what was going on. So yeah, like we're in a channel, and then I hopped in the channel just to try and talk with you, and then I was like, not sure why you hopped off. Maybe you're having issues with connectivity at home, so I don't know. Oh, your computer didn't. Okay, that's fair. That's fair. I will say that Discord worked. I saw your name on there. Okay, 100%. All right, so yeah, no problem, Lee Wen. Anytime. Okay, you come to me for help. That's what I'm here. That's what I'm here to do. I'm here to help you. Okay. Oh, I know that was that problem that we did together there, Lee Wen, was a little bit of a tough one, but glad we were able to push through that. So, then you're right. You just got to slow things down, and take it a little bit easier. Get the answer right the first time without all that mess. I'm not sure why. Like you could come on to Discord and I can just give you a call on Discord. Like if your name, it's like here. Let me show you what I'm talking about here. Okay. So this is the switch over here. So this is what I see on my screen. This Discord. This is the Discord here. And if your name is over here on the right hand side here, I'll see your name says Emma W. All right, just like your screen name there. Then which I did see today. I was like, oh yeah, I see your screen name, and then you just have to. I could just give you a call, or you just write a message in the general chat or whatever, and you can get my attention, and we could go over problems there together, Emma. Like that's not a problem at all. So feel free to just type stuff out in general chat. Says hey Professor Chibs, I need some help, and yeah, you got it. 100%. So it's not too big of a deal, I promise you. All right. Because I know you're registered and stuff. So again, as long as your name appears here on the right, then I know that you are in the Discord there. So yeah, this is exactly what I see. Yeah, of course, Emma. Oh yeah, that's fine. The reason why I like using Discord is because I can stream share with you. I can show you things personally and stuff. You know, if it's not working out for whatever reason, and I totally understand that, then yeah, we could just continue to email correspond with each other. That's fine too. It's just for me, it's like super easy just to kind of show you in real time and stuff. But I get it that we have issues. We have technical issues with the computadoras, so I don't blame you there. I don't want you to feel like you've been left out or anything like that. I promise you. Okay. All right. Hey, anybody got any questions before we get started here for today? I don't know if you have any questions, but we'll just we'll do it. What day will the exam be on this week, Emily? The exam it has already been posted there, Emily. On the exam has already been posted, so that's been ready to go for a while now. Um, as far as I know, the exam has been posted for chapters 2 and 3. Now, we haven't quite finished chapters 3 just yet, but we're getting pretty darn close to finishing it. So we're gonna get it finished it today, actually. But yeah, if you want to be like prepared for chapters 2 and 3, that will be there. But you can take the exam anytime as long as it's before the last day. That's right, Nick. That's correct. So I will say this though. Again, yes, Emily, the first exam has already been posted. I posted that like last week. So the other exams I haven't quite posted yet, but I'll be working on them this week. So basically, yeah, you could take it anytime before the last day of class. The only thing that I highly recommend though is get it done as soon as you get the chapters 2 and 3 done, because if you try and do procrastination, it's not going to work out very well. There are a lot of problems to do. So on the test, though, there's not a ton of problems to do, but there's a practice exam for you to try that'll give you a good idea about what the questions on the test will be, and then the exact time, exact exact things will be on there. So, is there a time limit on the exam once we open it? No, at least I don't think so. I never put a time limit on it, as far as I'm aware of. If there is a time limit, just let me know, because I don't think I set one. Question mark? I didn't find an option for it, in all honesty. So you just don't have any resources. Like the practice test, you have all the resources, and then the regular test, you don't have any of the resources. So that's pretty much the difference there. Um, are there any other questions? Hopefully, yeah. If there's any issues that come up for the test and whatnot when you give it a try, please let me know, so that way I can rectify those as quickly as possible. So the first time for me using the system with the test stuff there, so I don't know if there's anything I need to iron out. I want to be sure that, of course, it's going to be fair on you. I don't want to be like penalize you for something that's out of your control. So bring it to my attention, and I'll take a look at it and investigate and make any necessary changes. So again though, my suggestion is don't leave everything at the last minute. It's going to be a bad time. Everybody who's left stuff at the last minute, it usually doesn't end up to be good. The grade doesn't end up to be good. And yeah, like I said, I'm giving you every out possible, but it's on you to be responsible for getting it done in a timely manner. So I'm gonna leave it on you. The test and practice test. So they're not on the ECC site, Emily. They're on the web. They're on the Cengage site, where you can find all the online homework. So nothing is. Everything is online with the Cengage site there. So if you've registered for the homework there, you should see it also underneath the tests thing there thing. Oh, okay. No problem. I'm here to help. Hopefully I answer. I'm glad I hopefully answered everything. Sometimes I don't even know what I'm answering. I have to know what I'm trying to say. What are you trying to say? I don't know anymore. All right. So yeah, if you go to this, I'm gonna go show this off here. You go to this, and we go to like current assignments and whatnot. You get a list, and right down here you see the chapter 2 and 3 practice test and the actual test. So you can check on that, and then you'll see everything's posted. So should be good to go. All right. Anything else, anybody? Anybody else? Would you have any questions before we get formally started here for today? All right, we'll go ahead and get going here then. All right, let's do some intros and we'll get started, okay? All right, let's do some intros. All right, there we go, much better. Okay, let's get started today. Welcome back to Monday. Hope you had a nice weekend. All right, so for today, ladies and gentlemen, today we are going to pick up where we left off last time. Last time we did just a section here. And we did section 3.4. We did talk about marginal functions and whatnot. Okay, and we took a good chunk of time trying to get that done here. Today we're going to be going over the last two sections here of chapter 3 that is on the agenda. So I do intend to fully get through these, knock out these last two sections here, and then that'll be it for chapter 3. And these last two sections here are pretty fast in terms of its actual content material sort of thing. So let's talk about it, and let's see what we're working with. All right. Okay. So let's go ahead and put this a little shorter here. Alrighty, so we only have essentially two questions that we're going to be covering here that will cover both sections respectively. So in terms of actual things to write on your handout, there's honestly not much because we're just going to be applying, applying, and applying, and applying, and applying. So question number 1 talks about how do we do higher order derivatives? Okay, so essentially what we're going to have is we've talked about derivatives already. We know how to figure out derivatives on just the level with just a regular function. We'll also be exploring here not just the first derivative, which we've been normally doing all the way up to this point. We're also going to be exploring the second derivative, which is the derivative of the derivative. Now, where is this essentially used? Well, a very popular way where we actually use, say, first and second derivatives in a particular context is talking about physics. When you talk about physics, then these two guys are pretty much primarily used very often. So, for example, here, if they talk about an object or a particle, we have a position function, which is usually called s of t. Okay, that reflects the position of the particle at some point. Okay, if we take the derivative of that particular function, that position function, we get v of t, which is the velocity function. So how fast that particle or object is moving. And then finally, we can take the derivative of the velocity function, or in other words, the second derivative of the position function, and we get the acceleration function. Again, how fast that object or particle is accelerating. Okay. So this is a very common, again, way to kind of define where it's actually useful in a, you know, in an actual application at the end of the day. And so all we're going to be doing here is applying and applying and applying, and basically just going through this process here a couple times. And it's not, again, it's not too hard. It just takes a little bit of time to do. So let's go ahead and take a look at some problems here, and let's see how we can do them. Oh, is not the page I wanted. There we go. That's the page I want. All right. So let's start off with something basic, and let's just work our way up. All right. So we'll start with some basic functions here, and then we'll see what we get. All right. Okay, so here's our function. So we have negative 3x to the third plus 2x squared minus 10x plus 7. And all we want to do here specifically is we want to go ahead and find the first and second derivative. So let's find that. So what is the first derivative of this function? Let's just go down the line here. What is the first derivative of this function? What is the first derivative of this function? Anybody tell me? So just do the regular derivative here. I can sit here for a while. So, all right, there we go. Minus 9x squared plus 4x minus 10. Okay, good. All right. Excellent, excellent. All right. Now, let's ask what's the second derivative here? So basically, just take the derivative of the derivative. So if you could take the derivative of this previous answer we just found, what is the derivative of minus 9x squared plus 4x minus 10? What's that going to be? All right, good. Right, minus 18x plus 4. Okay, good. All right, that's it. So that's the first and second derivative, at least on a basic example. That's not too bad. All right, fine. Let's try another. Yeah. All right, so let's crank it up a notch here. All right. All right. So here we got x squared plus 2x plus 4 to the 5/2 power. All right. So let's take the first derivative of this function here. What is the first derivative here in this case? What do we get for this first derivative? All right. Okay, 5/2 x squared plus 2x plus 4, 2x plus 2. Okay. 5 x to the 3/2. All right, we're pretty close. All right, so those two answers there are very close. So I'm going to agree with most of this. We're missing one part here. So all of you are missing the same part here. I see each one of these three answers, and it's missing one part. So I agree with everything here, but we're missing something. I'm missing this exponent up here. So what's my exponent? There we go. It's to the 3/2 power. That's correct. The exponent 3/2, right? So that's what I'm missing there, right? Because you have like Elizabeth, you had 3/2 here, but that was kind of on the outside. That wasn't to the inside there. So okay, very good. All right, so we definitely have that. That is the first derivative there. 100% correct. Now, in this particular case, there are a couple ways you can kind of approach this. If it helps, you can go ahead and simplify a little bit here in order to make sure that the second derivative goes a little bit more smoothly. So for example here we got 5 halves and 2x plus 2. If we go ahead and multiply the 5 halves with both the 2x and the 2 here, what we're going to have is we can rewrite it as x squared plus 2x plus 4 to the 3 halves, so that's not changing. And then this would modify to 5x plus 5. So again, the 2's cancel out, just leaving you with 5 here. And if you want to leave it like that, that's fine. We're just trying to simplify it to make it easier to do the second derivative. Because sometimes, and this is a good case of where this happens, the second derivative is going to be a little bit messy. So just kind of cleaning things up here may be, again, in your best interest. Even though we want to avoid the work a little bit, sometimes we just do a little bit of legwork here to not have to deal with something too crazy. All right. So now if we're doing the second derivative here in this case, what are we going to be using here to find the second derivative? What should we use here in this case? We're going to find the second derivative of this function. Our go-to here. What kind of rule are we going to use here for the second derivative? We have to use the first derivative to get the second derivative, so what rule are we going to be using here in this case? Yes, the product rule. Okay, very good. That's correct. Okay, so we're going to go ahead and use the product rule here. So this is going to be our F, and this is going to be our G right here. Good, good. Okay, so again, if we want, again, we're going to use, again, F prime G plus F prime G plus G prime F. All right, that's right. It's the product rule. That's correct, Leewin. All right, so let's go over each one here. Let's go over the derivative here. What's the derivative of F? What's the derivative of this first guy? What's the derivative of F here in this case? X squared plus 2x plus 4 to the 3 halves. What's that derivative? Derivative of G is really easy, by the way. Derivative of G is 5, so that part there is not so hard. Just need that derivative of F, and then we can start just plugging in inside our product rule there. Should be good to go. All right, that's correct. All right, very good. Oops, I meant to put it on the other one. So right, this will be 3 halves x squared plus 2x plus 4 to the 1/2 power, and then times 2x plus 2. All right, that's correct. Nice. So now all we have to do is go ahead and just plop in everything that we have found here for the second derivative, and we should have our answer. So we have f prime g. So again, f prime here is exactly what we have down here. So let's put that in. Okay. All right, very good, Leewin. All right, so we have 3 halves. We have x squared plus 2x plus 4 to the 1/2 times 2x plus 2, and then we have that times g. That's the 5x plus 5 here, plus g prime f. So g prime here is 5, and f here is everything that we had to start with. So again, not much is changing. Again, that x squared plus 2x plus 4 to the 3 halves. Okay, and that is going to be our final answer for that. So again, some problems here will be a lot more involved than others into finding the second derivative. Again, you can keep going. Again, there's third derivatives, fourth derivatives, fifth derivatives, and so on. So you could keep finding the derivative of this function here. Obviously, I'm not going to find the derivative of this one. Here's easy, but you get the general idea. If you want to keep going, you can. You can keep finding the derivative until you got no more. So that's perfectly fine. All right. So we have the basics of it at the very least. Any questions about at least the basics here? This turns in because I multiplied 5 halves times this. So if you distribute here, Nick, essentially you have 5 halves times 2x plus 5 halves times 2. So the 2's will cancel out, and that just leaves you with the 5's. All right, no problem. All right. Any other questions before we move on? Hopefully that's okay. There I need to get to. Okay. All righty. All righty. So let's take a good look here at some other problems. I'm going to bring this up here. No, makes sense. All right, good. So let's bring up some other problems here. We're going to take a look at just again some applications that you can do here. So let's look at an acceleration of a car, for example. Okay, so yeah, we'll do a couple of these here. So the distance s in feet covered by a car t seconds is given by s is equal to negative t to the third plus 8t squared plus 20t. All right, t is between 0 and 6. Find a general expression for the car's acceleration at any time t. Show that the car is decelerating after 2 2/3 seconds. So seems rather specific about what it would like, but in reality what it is actually asking for is pretty straightforward. Okay, so let's talk about what this is actually asking us to do. In our case here, what it's actually asking us to do is it's actually asking us to go ahead and uh, pretty much take the second derivative. If we go back to our initial thing here, we have the velocity function, we have the acceleration function. Okay, we see the acceleration function is the second derivative of the position function. So because of that fact, we're just going to take our position function here, which is our s of t, which is given as negative t to the third plus 8t squared plus 20t. And all we're going to do here is just simply go ahead and find that second derivative. So let's find the first derivative here. again, if we find the first derivative here, that is specifically going to be negative 3t squared plus 16t plus 20. Okay. If we find the second derivative here, s double prime of t, again, that's going to be the acceleration function here. That's going to be specifically negative 6t plus 16. Okay. So we have that. There you go. So what it's essentially asking us is show that the car is decelerating after 2 2/3 seconds. Now, mainly that's a very specific number, but all they're asking us to do here is to go ahead and take it s double prime of 2 2/3, which is the same thing as 8/3. Again, that'd be 8/3, whichever way you want to write it. Just going to put negative 6 times 8/3. Okay, plus 16. All right. And so here we get, let's see, negative 6 and 3. 6, 3 is 6, 2 times. Okay, so we have negative 2 times 8, so that's minus 16 plus 16. The answer here is 0. So the acceleration for this car is 0. So it would indicate that at that point here, all right, the car would be decelerating at that particular point. Okay, so it's no longer accelerating. If the acceleration is 0, it's no longer accelerating, and it'll hop over to a negative deceleration after that moment in time, which means you are basically pumping on the brakes. So it's like if you took your foot off the pedal, it isn't getting any faster. All right, and then if you hit the brakes, it's going to decelerate after that point of 2 2/3 seconds. Okay, so going fast, and then 2 2/3 seconds pass, and then it slows down. It comes to a stop after looks like 6 seconds or whatever. So, okay, any questions about that? Okay, let's try another one. Try another one. Yeah, not that. Okay. Let's take a good look here at this one here. Okay, so let's look at number 32 here. Okay, so Alzheimer's disease. Okay, so as baby boomers enter their golden years, the number of people afflicted with Alzheimer's disease is expected to rise dramatically. In a study published in the Journal of Neurology, the number of people with Alzheimer's disease in the United States aged 65 and over is projected to be X amount, okay, this function here, million in decade T, where T equals 0 corresponds to 2010. All right. Letter A, what is the projected number of people with Alzheimer's in 2030? Okay, so in 2030 here. So that's 2 decades after 2010. So the first one here is just asking us, okay, let's go ahead and let's put this down here. Sorry. Um, just a second here. Come on. Oh, I hate when it does that. It's very annoying. All right. Book is not super friendly when it comes to like wanting to be. Have to figure it out somehow. There we go. Have to work with what I got. All right. Let me write this function down actually. Make this a bit easier, guys. I don't know why the book doesn't have a scroll over feature, the right and left. Really bad. Ain't gonna lie. Oh All right. Get this trying to oh my god. All right, give me a second. Apparently, I don't know what I'm doing about half the time. All right. This is 32 NFT. I have 5. All right. So the first one here is T is going to be equal to 2, which reflects the years 2030. All right. So again, 2 decades after 2010, that's what T will reflect. So if we plug in 2 in for this function here, we're just gonna see what we get here. So we get 0.00525 times 2 squared plus 0.075 times 2 plus 4.7. All right. Again, we'll just plug that into the calculator here, and I'll just plug it in really quick in mine. So 0.00525 times 2 squared, 0.075 times 2 plus 4.7. All right, so put this all together here, and if you did this right on your calculator, you should get 4.871. That should be your answer for A. All right, no problem. All right, so that's pretty easy. All right, let's go ahead and read off letter B here. Letter B says, how fast is the number of people with Alzheimer's in the United States growing in 2030? All right. So how fast is this going to grow here? So in the year 2030. Okay. So let's take a look here at this one. So in this case here, how fast is the number growing in 2030? In this case, we have to take the first derivative of this function here in order to figure out how fast it's growing. So if we take the first derivative here, we just take this 2, bring it outside. So we do 0.00, we do 2 times 0.00525 times t plus 0.075. All right, so again, just doing that out here. So here we get 0.0105t plus 0.075. And we're just going to go ahead and plug in 2 in for that. Okay. All right, so here we get 0.096. So 0.096 is what we get here specifically for that. Okay, good stuff. All right, so far so good. All right, yeah. Okay. And I think I want to check one thing here actually really fast. If I recall correctly, this part there has brick. That does. Okay, that's. Is that true? Hang on just a moment, guys. I want to be sure it's not doing one thing here. Okay, that's fine. All right, that's okay. All right. Okay, so then the last part here, let's talk about the last part then. Letter C says, how fast is the rate of growth of people with Alzheimer's age 65 and over projected to change in the period covered by the study? So how fast is it projected for the period covered by the study? So this is from 2010 to 2050. So it's from 0 to 4. Okay, so if we want the rate of change here, in this particular case, we could also see we can also go one better, or we can do, there's a couple of ways we can see the rate of change here um, at this particular case. So the rate of change at, the rate of change over at, rate of change over, okay. We're going to do n prime of t divided by n of t. We could also do n double prime as well. So I guess we could do that. Going to be from 0 to 4, so we could do n double prime of 4 here. So if we do it ahead and do that here, let's go ahead and see what we get. We get 0.0105. No, that's not right. Gotta do it the other way. I gotta take that back. Sorry, guys. I'm gonna do that this way. N prime of 4 divided by n of 4. That's what. We're going to plug in some numbers here. We're going to see what we get here for how far it's going to actually go. So again, just plug in 4 into our functions here. We're going to see what we get. So again, n of 4 here, yeah, predicted to change in the period covered by the study. Hang on a sec. Do I want the period study, or do I wonder if they want 4 or they want 2. You're going to do the same thing regardless. So it's just a number change, basically. I think I'm gonna, let me change this then. All right. This one here, this one's actually a little bit not great word. All right. Let's just do 2, and I guess we'll just cut it down the middle. So here we would get literally n prime of 2 would be 0.096 divided by 4.871 if we were to cover this portion of the study. So then we would just go ahead and modify that out. All right, and so here we get 0.0197. Okay, so if we were to do it over those first 2 years, we can just take the previous 2 results and put them together just like so. All right, so we have that. That's all well and good. Okay, good stuff. Okay, any questions about that? Hopefully that's not too bad. Okay, let's go ahead and do one more here from this particular section. I think there's yeah, let's do that one. That's fine. Let's go ahead and do number 38. Okay, so 38 is going to be the last one we'll do here. So it'll be the test flight of a VTOL. All right, so 38 says, in the test flight of the McCord Terrier, McCord Aviation Experiment VTOL vertical takeoff and landing aircraft, it was determined that T seconds after liftoff, when the craft was operated in the vertical takeoff mode, its altitude in feet was this. So this was the altitude here. Find the expression of the aircraft's velocity at time t. All right, find the velocity at certain times. Find the acceleration. Find the aircraft's acceleration. Find the height. Okay, so we're going to do a couple of these here. Let's at least write down the function. I'm just going to, again, state the function here on our paint tool. And we'll answer the question. So given h of t here in this case, this is 38. All right, and that's 1/16 t to the fourth minus t to the third plus 4t. Okay, so they ask us to find the velocity function here first. That's what we want to do in part A, find the velocity function. So what is the velocity function going to be? How do we find the velocity function again? What should we do? All right, h prime of t, good. So we're just going to find that first derivative there. And what is our first derivative? That's correct. So what's our first derivative there? Okay, that's correctly went. Is our first derivative going to be then? What are we going to get here, folks? I just want to know. I can wait, that's fine. All right, 1/4 t to the third minus 3t squared plus 12t squared. Oh, that's closely went. I will agree with the most of that. 1/4 t to the third is correct. Minus 3t squared is correct. Plus 8t. Okay, plus 8t there. Yeah. That's 4t squared, not that's 4t squared, not 4t to the third. I think that's where you were off there. That's okay. All right, good. Now, what it does ask you is to go ahead and find the velocity at certain values. You can go ahead and plug in these values, again, 0, 4, and 8. That's really not too bad to do. They're just basically asking you, hey, just plug in these values here. You can plug it into the function that you have here. Now, it does ask you here for part C to go ahead and find the acceleration function here. All right, there we go. So we're just going to find the second derivative here of the height function. All right, so what's the second derivative here of this function? That over then. All right. 3/4 t squared. Okay. I had to check something on my phone there. All right, it's 3/4 t squared minus 6t plus 8. That is correct. Okay, very good. And what it does ask you here specifically is it's going to ask you for like values of like 0, 4, and 8 to plug into this function as well. So as long as you know the first and second derivatives here, again, from your position function here, in this case, the position being the height, that's again just a different definition, you're going to be able to find that no problem. Okay, very good. All right, nice work. Okay. All right. Any questions about that? Hopefully that's not too terrible. Some of the other questions can be a little tough. We'll try. Actually, we'll look at one more here. I think one more is okay here. Just to look at the second derivative here. Let's look at 40. Or actually, no, I take that back. Let's look at 41 because that's a slightly different look at that. So it's 10.72 times 0.9t plus 10 to the 0.3 power. Okay. So that here, 10.72 0.9t plus 10 the 0.3 power. Okay. Now, we're not going to plug in any numbers in here, but all I'm going to ask you to do here is just find me this second derivative. All right, that's what I would like you to do. Now, the first derivative here, I'm going to let you know how to do the first derivative. So the first derivative here, it can be a bit tricky, but once you understand how it's done, there's really no difference in how we've done it before in the past. Literally no difference. So again, this do understand that 10.72 is literally going to do nothing. Okay, it's just a number that kind of sits there. It's really what happens to this 0.3, and of course it's on the inside here because we're going to do a slight modification of the chain rule. So doing that here in this case, we're going to take that 0.3, we're going to bring it outside. So we're going to take 10.72, multiply that by 0.3. We're going to keep the inside the same, right? So again, just doing the chain rule here. And the power will change here. We're going to take 0.3 and we're going to subtract it by 1. So here we're going to get that to the negative 0.7 power. Okay? But we also have to multiply by the derivative of the inside here, which is 0.9. Okay? So if we look at the first derivative here, this is what we have here so far. Okay? Now, this looks really ugly. Okay? And it does. I mean, realistically, it looks pretty ugly. But again, this is one of those things that we talked about earlier. Hey, we got a bunch of numbers that are multiplied by each other. Let's just clean it up and just make it easier for ourselves and see what number we get on the outside here, so it's easier for us to take the derivative of once we put it all together. So if we take 10.72 times 0.3 times 0.9, then here we're going to get 2.8944 times 0.9t plus 10 to the negative 0.7 power. So just a slight cleanup here, but not by a super large stretch, I promise you. Now, if we want to find the second derivative here, let's do the second derivative. So the second derivative will be pretty much the same like the first, at least in its approach. So all we're going to do is we're going to take that minus 0.7, bring it out in front. So again, we get 2.8944 times negative 0.7. We can keep that inside the same. Subtract by 1 from the exponent, so we'll get minus 1.7. And then multiply that by, again, 0.9, which is the derivative of the inside. And here, just putting this together, just going to go ahead and get 2.8944 times negative 0.7 times 0.9. Here we get negative 1.823472. And this is going to be our second derivative of our function. All right, so even with decimals as our exponents, this is our second derivative here. And again, it's in this problem here, it'll ask you, hey, plug in a number, tell it what it means or whatever. But there you go. That's pretty much all you want to do for that, essentially, to find the hardest part of the problem here, which is essentially finding that second derivative. So just another example here about how to find that second derivative with slightly tougher numbers. But in all honesty, you're not doing anything different than you were from before. Okay. Alrighty. Any questions about that? Ah. Where did the 0.9 go? It was multiplied here together. This was multiplied with the negative 0.7 and the 2.8944. It was multiplied all together. Again, that was just a number on the outside there, Nick. So this multiplied with this and this. Any other questions? No? Okay. All right. Oh, okay, it's about break time here. Okay, let's take a short break. Okay, so we're going to come back in about 10 minutes at 7:10. And then we're going to do the next part here, section 3.6. That is what we're going to be doing here. All right, so we'll come back here in section 3.6. That'll be the next section here. Hopefully we'll get that done. So let's take a short break and go ahead and do that. All right, we will be back 7:10. All right. All right. We are back. All right. We are back. Love that. All right. Okay, we're back. Okay, let's go ahead and get started here with the second half of class. All right. And we're going to go ahead and do the second question here, and we'll do some stuff that I do promise you. All right. So let's talk about what we need to do here next. Let's do number 2. All right. We're going to go to the big board here. Okay. So let's take a good look here at this. All right. So let's do question number 2 here. Question 2 asks, how do we do implicit differentiation? Okay. So how do we do implicit differentiation? All right. So that's what we're going to be talking about here in section 3.6. Is what we're going to want to find here is we're going to get equations here in two variables, in x and y. All right, and we want to solve for what we like to call dy over dx. The derivative of y with respect to x is another way of saying dy over dx. So actually, we'll put that down because probably slightly. So y over dx is the derivative of y with respect to x. Okay? So what's the trick in doing these problems? The trick is that anywhere we take the derivative of y, we're going to put a dy over dx next to it, and then solve for dy over dx. Now you're probably saying, what the heck does that mean? What do you mean by that? That doesn't seem to make any sense. All right. Well, we're going to go ahead and apply this and see a lot of different variations of where we're going to use dy over dx. And yeah, see what we get. Cool enough. All right. Okay, so let's look at the first example here. Be a simple example. Then once we start ramping up these examples here, they won't be so easy. You have to be a little bit extra careful. Okay, so let's take a look at this example here. We have x squared plus y squared is equal to 16. All right. So what we want to do here first is we want to go ahead and take the derivative of each respective variable. Okay, so what we want to do here, just let's take the derivative of each respective variable here. So meaning to say, all right, well, we have the derivative of x squared. And if we take the derivative of x squared, just using their plain Jane power rule, that's going to be 2x. Okay, that's it. Fine, 2x. That's okay. Now we look at y squared. And you're like, okay, I'm going to approach y squared the same way I approached x squared. What if I took the derivative of y squared? Well, the derivative of y squared is going to be 2y. But now that I've taken the derivative of y, I'm going to slap a dy over dx next to that guy. Okay? So because I took the derivative of y, I'm just going to tack on a dy over dx next to that guy. And if I take the derivative of 16, well, the derivative of any number is 0. So this is what I get here so far. Okay. Now, again, just as a simple problem here, we're just going to approach the same trick here, meaning to say, all right, treat dy over dx as a variable. All right, just say that it's dy over dx. It's some random variable that we want to go ahead and solve for. So everything else needs to just follow some simple algebra to solve for that dy over dx. If it helps, put some parentheses around that dy over dx so you know that is, a guy that you're going to basically isolate at the end of the day. So all we're going to do is we're just going to subtract by 2x on both sides first. And so we're going to get 2y dy over dx equals negative 2x. Then we're just going to we want to solve for dy over dx. We're going to just divide by 2y on both sides. In this case here, because we just want dy over dx is in terms of something. So yes, your final answer here will certainly be in terms of both x and y. Okay, so it's not just going to be necessarily always in terms of x. Not in these cases. So just Simplifying here, we get dy over dx here. 2 and 2 will cancel out here. This leaves you with negative x over y. Okay, and this will be our final answer for that problem using implicit differentiation. Okay, any questions about that so far? Oh yeah, we're doing more. Elizabeth, we're doing much more. I just want to be sure that at least you understood the basic premise here first. I promise. We got a lot more to do. Casual panic indeed. No, Elizabeth, I'm just gonna leave you hanging for the rest of the time. You figure it out on your own, okay? You're on your own. Here you go. Right? I'm gonna be that guy. Ah. You're all on your own. I'm out. Okay, I'm out. Everybody, see you later. Okay, bye. I'm just kidding. I'm kidding again. All right. Um. Okay, so let's do the next one here. We got the next one here definitely to do. All right, now we're going to ramp it up just a little bit. All right, so now we have x squared plus 5xy plus y squared is equal to 10. All right, so this is what we want to do. We want to solve for dy over dx using some implicit differentiation. You're probably wondering how we approach this. Well, the tricky part here really stems from the fact that of the middle part that you see here. The middle part that you see here really is the toughest part. So what we do is we want to take the other parts here. We have x squared. Again, we're just going to approach it the same way. That's going to be 2x. Nothing changes. On the end here, we have y squared, just like we did last time here. That's going to be 2y dy over dx because we took the derivative of that. Actually, I probably should have afforded more room, but it is what it is. All right. And this is going to equal 0. Now, the real question is what happens here in the middle? All right. We have 5xy, and we need to find that derivative. And that derivative there is not going to be quite as easy as it may seem. Now, the reason is because in this case, we're going to use the product rule in this instance because we have x and y here. Again, treat x and y as two separate kind of individual variables. In this case, again, we have x times y. So imagine if you put some parentheses around 5x. Imagine if you put some parentheses around y. Again, you have like one function containing x multiplied by another function that contains y. And we're going to go ahead and find, in this case, the product rule behind 5x times y. So what we have here is, again, if we look at 5xy here specifically, 5x times y, we take the derivative of the first, which is the derivative of 5x. Derivative of 5x is 5. Remember, that's f prime g plus g prime f. We have 5y. Again, if you wanted to call this f and g, that's fine. You have f prime g plus g prime f, just as a friendly reminder. Then we take the derivative of y. Now, the derivative of y is technically 1. That part is definitely true. That's would be like the derivative of y is 1. But since we took the derivative of y, we have to tack on a dy over dx next to that. And then we have f here, which is the 5x. Okay, so if we just simplify this just a smidge, just to take out the 1, because it's not really much of a point, then this is what we have here. We have 5y plus 5x dy over dx. Okay, so that's that middle term right here. We have 5y plus 5x dy over dx. Okay. Any questions about that? Middle part there. Any questions about the middle part? Hopefully everybody has that portion down. We're not done with the problem yet, but as long as everybody understands where we're getting this stuff from, okay. Okay. Now, the next part here, again, we're going to start from here, the 2x plus 5y plus 5x dy dx plus 2y dy dx. We got to solve for dy over dx. Let's see, Elizabeth has a question here. Why is there a 5 in front of the y? Because you took the derivative of 5x. So f is the derivative f we have here. If you take the derivative of f, the derivative of 5x is going to be straight up 5. That is why there's a 5 in front of y. F prime g is 5 times y. Right? So again, if it helps, write out those rules, okay? Write out the product rule, write out the quotient rule if you got to use it in a circumstance or whatever. Doesn't matter. But write out the rule here so you know that where you're putting in those numbers and plopping them in. If you're having a tough time visualizing the product rule, not a problem. That's why I make the rule easier to kind of memorize. That way you're like, okay, it's f prime g plus g prime f, and then you just like define your f and g and then plop it in. And sometimes you just need the visual side of things, and it makes it a bit easier to do. So, yeah. Any other questions before we move forward? Any other questions before we move forward? Sure, we got that down. Okay. Okay. So, next, let's look at this here. All right. So let's rewrite here. We have 2x plus 5y plus 5x dy over dx plus 2y dy over dx. Okay, so the way we're going to solve for dy over dx here is we're going to move everything that is not dy over dx. We're going to move that over to the other side. Things that are not dy over dx, let's move them away. Okay. So here we have, again, 5x dy over dx plus 2y dy over dx equals negative 2x minus 5y. Now, dy over dx, specifically here, dy over dx is going to be, again, what we want to solve for. So in order to get that to happen, we're going to factor out a dy over dx here. So if we factor out a dy over dx because it's in both of these terms, sorry about that, it's going to be 5x plus 2y. We have dy over dx, and then we have 5x plus 2y left over. What this will allow us to do is to divide out by 5x plus 2y on both sides to get our final result here. And this is going to be our final answer for this problem. All right. All right. Any questions so far about that? Hopefully that's not too terrible. It's too early for this? Well, I don't know what to tell you. How is it too early? It's 7:30 at night. that means that means in about 30 minutes it might be too late. I see. Am I blaming you for feeling that way? Absolutely not. Do I still have to do it? Absolutely. Do I have a choice? Absolutely not. Sometimes, folks, I don't have a choice. I kind of have to do it because I have to do it. Sadness. Sadness for all peoples involved. All right, I'm gonna do another one here. Let me look at the homework problem for that, actually. See if there's another variation of the homework problem that I want. All right, that one I just did. That one's pretty similar. Okay, let's do that one. That's fine. And we have the tangent one and then that one. Okay. Okay. All right. Let's do this one. All right. Let's show off a homework type problem here. So some of these are pretty similar to what we've just done here. No problemos. But probably the one that will be the toughest here. Probably number 5 and 7 will probably be the toughest. All right. Let's look at number 5. We'll actually use these exact numbers, and these numbers may be different for you, but at least you'll see how this works. So, smaller, bigger. Okay, clear out everything together. All right. All right, so doing this together here, we're going to have 4x plus 3y to the 1/3 power equals x squared. All right, so this is the part of the program where there will be a lot of hate mail thrown my way, but you know what? So be it. All right, so Elizabeth, if you have a knife out behind your back, which I am going to make a solid assumption you do, just going to roll with it, okay? Now, she's like, I'm going to pounce, I'm going to stab you. Okay, that's perfectly fine. I totally get it. All right. I wouldn't blame you in the slightest, and I would bequeath you all of my $5 in my pocket. So that'll work. All right, so what we're going to do here is we're going to take this 1/3 here, we're going to bring it outside. So essentially, let's just take the derivative of everything. Here we take the derivative of x squared, that's 2x. The derivative of this guy here, we're going to do the chain rule. Okay, so we're going to keep the 1/3 here of 4x plus 3y. I'm going to need more space. Just all right, so we're going to do 1/3 4x plus 3y. That part is true. All right. If we subtract that off, then it would be to the negative 2/3 power. All right, so again, doing the chain rule here, then we do the derivative of the inside. Now the derivative of the inside here is going to be 4, so that's derivative of 4x, plus, and then derivative of 3y here is 3, but since we took the derivative of y, that's going to be dy over dx. Okay? And then this is going to equal 2x, which is the derivative of the right-hand side. All right? Again, what's our goal here? Our goal here is to get dy over dx by itself. All right? So, yeah. Where did I get the negative 2/3 again? That's because we took the 1/3 and brought it out front. And remember, the power rule says that if we bring the 1/3 out front, let's put the red line here, we have to subtract that by 1, right? woke up and chose for the derivative of a letter to be 4 letters. Well, does it start with the letter F or does it start with the letter S? It could start with the letter C. I don't know which one of those you want to choose, but either way, I don't think you'd be wrong. you, you get your pick of the litter, Elizabeth. I don't know which one you want. We're gonna. I just know one of them's gonna just roll with it. Oh my gosh. All right. The question was how we got negative 2/3. We got 1/3 minus 1 here again. 1/3 minus 1 is going to be 1/3 minus 3 over 3. That's going to be negative 2 over 3. Okay. So that's how we get negative 2/3 there as our guy right there. Oh man. All right. So what we're gonna do here first is we need to go ahead and well we need to solve for dy over dx doing some clever algebra. Well, how do we do that? Well, let's take a gander and how that's gonna work. And it's gonna be not so nice, but it works, even if it is not so nice. All right, so the way we want to do this first is we want to go ahead and move this 1/3 over to the other side. So let's multiply by 3 so we can cancel it out on the left-hand side. We'll just multiply it on the right-hand side. So, we'll just deal with something here. It's not the greatest in the whole wide world, but whatever. It is what it is. So I haven't done anything too fancy just yet. But all right. So here we get 6x on the right-hand side, okay? 2x times 3. Now we want to go ahead, we still want dy over dx, so we need to divide out by this entire expression here of 4x plus 3y to the negative 2/3. We remove it from the left-hand side and move it to the right-hand side. So don't want that stuff hanging around on the left-hand side since dy over dx is over there. That's the last guy we really want to be dealing with. So not our good friend. We're just gonna move it across. All right, so that leaves us with 4 plus 3 dy over dx. Okay, that's what it leaves us with. So what we're going to do next is we're going to go ahead and subtract 4 on both sides. All right, so we're going to subtract 4. Again, let me showcase what this is going to look like here so that way it's clear as day about what this maneuvering is doing. Dy over dx here is equal to 6x over 4x plus 3y to the negative 2/3 minus 4. Okay? This is what we have here so far. Finally, we want to go ahead and divide by 3. Okay, because we have a 3 here, so we're going to divide everything by 3. That way these 3's cancel. We're going to divide everything by 3 here as a result. Now this, of course, I'm not going to lie, looks fairly ugly, so we can simplify it just a smidge. We get 6x over 3 times, this 3 gets slotted down here, by the way, when you divide. So this 3, it will be 3 times 4x minus 3y to the negative 2/3 minus 4 over 3, that's what we get here. This 6 and 3 will cancel, this will leave us with 2. So we're going to end up with the final answer of, as bad as it looks, is the final answer. The final answer for dy over dx is going to be 2x over 4x minus 3y to the negative 2/3 power minus 4/3. Okay, and that's our final answer for that. Good stuff. Okay, any questions about that? Hopefully that is okay. This is what we get for that. I'm very lost. I know there's a lot of manipulation here, Nick. Of a lot of manipulation here for this particular problem. So one of the things I would suggest to do for this one is just kind of watch the replay here a few times as I kind of go through it kind of one at a time here. I know that at first when you look at this, it looks like a complete disaster, but you'll notice that I'm just basically taking it one piece at a time and essentially just kind of isolating the dy over dx at the end of the day. So again, just to recap here though, I did the chain rule on the left hand side. That's what I did, the chain rule there. Again, so once we took the derivative of y, we slapped we put a dy over dx here. That was, we took the derivative of 3y, that's 3. Then we put a dy over dx next to the 3. Derivative of the right hand side, it was 2x because that was x squared and there wasn't much going on there. And all we had to do is get dy over dx by itself using some algebra by moving stuff around. And that's essentially what the majority of the steps were, just moving stuff around to solve for dy over dx at the end of the day. So yeah, I'm not going to disagree with you, Nick, that being lost here when you first see it. So does dy over dx always go to the next to the y variable? No. Let me explain here. Okay. Let's go back to the notes here for just a second. The trick to this is, and I'll put this underlined here. Read this carefully, so because this can be a little tricky. Anywhere we take the derivative of y, so it's not anywhere where y exists. It's anywhere we take the derivative of y, we put a dy dx over next to it. So if we don't take the derivative of y, then okay. So if the last example we had 5xy, and the first one we took the derivative of 5x, and that was 5. We didn't take the derivative of y there. That's why there's no dy over dx next to that. Again, anywhere we take the derivative of y. The Leeway said, why is the first one 1/3 4x and not 1/3 5x? So again, you have to do the chain rule, Leeway. So let's go back here for a second. You have to do the chain rule here. So you got to do the derivative outside there. The derivative of the outside, you have to do, again, you have to take that 1/3 and you keep the inside the same, the 4x plus 3y. So that's why it's not, you're trying to do two things at once, Liwen. What I'm trying to say, you have to do the chain rule just like you did before. Okay, Liwen? You have to keep the inside the same. That's going to be to the negative 2/3 power. That's the outside done. Then you do the inside. That would be the 4 plus 3 dy over dx. So that's why I'm not putting that together in that regard. Again, do the chain rule in its two steps, outside, inside, okay? Always chain rule is always outside, inside, outside, inside, okay? I want to be sure that you guys understand about why I'm doing these steps in this order, so it's not like it's coming from nowhere, okay? I'm doing the same exact rules as I was before, but I have that trick. Whenever I take that derivative of y over dx has to go there. Has to go there. Has to do things. All right, so important to have. All right. I do have to, excuse me. I do have to look at the next example here. I may show this off next time, number 7, but I want to show off this one here, which is number 8. I'm kind of running out of time. So if I get through this example here, then I'll show off 2 more examples from this section for next time. So that way you guys have your bases covered here for the homework problems. And that'll be the end of chapter 3. So, all right, but I do want to show this one off here because it says find d squared y over dx squared by implicit differentiation. All right. Okay, so let's do this one here. So we have x to the third plus y to the third equals 9. All right, so let's do that. Okay. Now, what we're trying to find here is d squared y over dx squared. All right, so this is what we want to go ahead and find here. Now, basically, what is this essentially? What does this notation here essentially reflect? This notation here essentially reflects the second implicit differentiation. All right. Now, you're probably saying, how do you go ahead and find the second implicit derivative? Well, you just got to solve for dy over dx the first time, and then once you solve for dy over dx the first time, you do it again a second time. And so, yeah, that's all you're doing. Yeah, I know. So basically, you're gonna solve. The trick here is to solve for dy over dx. You're gonna solve for dy over dx twice. All right. So let's just go ahead and do this here. Here we get 3x squared. Again, that's the derivative of x cubed. Plus 3y squared dy over dx. Okay. Equals 0 because, again, the derivative of 9 is 0. Again, we have to solve for dy over dx. So we're going to subtract by that 3x squared on both sides. So we get 3y squared dy over dx equals negative 3x squared. Now we divide by 3y squared. That's perfectly fine. All right. And we get our dy over dx if we just simplify just a smidge. We're going to get dy over dx equals negative x squared over y squared. Great. Sounds good to me. Okay. No problem. Easy peasy lemon squeezy. Now, next thing we want to do is now we want to solve for dy over dx for this particular problem. And we're going to get our final result here for the d squared y over dx squared. Okay, so now we got to do it for this guy. So in order to do this for this guy, there's several options that you have here. You could do the quotient rule. You can do the product rule here if you want to. There's several ways you can approach this problem. Let's say we did the quotient rule here. Again, we have f prime g minus g prime f over g squared. Actually, let me think about that for a moment. Let me assess that. Would that be easier? Question mark. That would probably make it harder. Probably make it a bit harder to do. Oh, okay. No, it would be fine. No, that'd be fine. I guess either way you could do it. Either way, it would be fine. All right. Well, let's just define each one here. Here you have f, and here you have g. Here we have f prime here is going to be 2x. Our g prime here is going to be 2y dy over dx. Okay, now I do want to point out what's going to be happening here because the next part here may look a little confusing. So I'm going to go slow over this next part here to get to our final result. Okay, even if you use the product rule, it's going to look a little confusing admittingly. Either way, you know what? Either way, I want to showcase this off here. Okay, so on the left-hand side, when we take the derivative here, we get exactly what we want here on the left-hand side. This left-hand side will be the d squared y over dx squared. Okay, so that's not going to change. The right-hand side, now if we do f prime g over g prime f, we're going to have negative f prime g, so f prime is 2x y squared. All right. And then we have, actually, here. Okay. And here we got 2x squared y squared, and then minus g prime 2y dy over dx. All right, times f, which was x squared, all over g squared, which was y to the fourth. Yeah. All right, fine. This is what it is. All right, it is what it is. There's only one more thing that you'll need to do here. Only one more thing. You're probably saying, man, you're already torturing me. I'll be like, yep, I totally am. All right. The last thing that we need to do here is, if you see here, we have a dy over dx, okay? That part is true. That dy over dx that you see there has already been defined. Remember that we solved for dy over dx in the previous part. That was negative x squared over y squared. So we're just going to play a little substitution. This dy over dx is negative x squared over y squared. And so we use the previous result to get the subsequent result for dy for the second derivative. So putting this together here, as ugly as it looks, which it is pretty ugly, we simplify it a little bit here. We get 2x squared, 2xy squared over y to the fourth. Just split it up into two fractions. Oh, has to. All right, you know what? I'm making this harder than it needs. Hang on. Hang on, folks. I'm making this so much harder than it needs to be because it's negative of this. All right. We have minus, let's see here, 2xy squared. Let's clean this up a bit. That'll be minus, this 1y will cancel out here. This minus minus, so this will become plus x to the fourth, 2x to the fourth over y, all this over y to the fourth. Boy, that looks terrible. All right. All right. Maybe I should have gone with the product rule. That probably would have been easier. I was thinking this through in my head, and I was like thinking that this would be a bit easier to do in my head with the quotient rule as opposed to the product rule. But maybe I was wrong about that, but that's okay. X over y squared. If you do this out even further, then you're gonna get. I'll show you what you would get here if you just simplified it out. You get this, and then you get, oh, that should be minus, not plus. Minus 2x to the fourth over y to the fifth. So if you simplified it further, this is what you would get here. All right. Okay, there we go. Got that last one done. I'm going to do those last two examples there on tomorrow, on Tuesday. All right. Any questions about the second implicit differentiation for this particular part? You get what I'm trying to do and how to do it, but I always fumble the steps. I totally understand. Let's just do a little bit more practice there, Nick. I know. At first, look, it's like anything. It's just take baby steps. That's how I did it too. Okay, that's how I learned, for example. I take baby steps. It doesn't don't try and rush the problem. So, if you're fumbling the steps, just take it one at a time. You know, there's no reason to try and make super logical leaps. You know, that's like I said, that's how I got to be more consistent. And it's just little by little. I always encourage people to do that because it's a lot easier on the brain. So I don't want to make things too difficult on the head. We have to think of 3 things at the same time. Like for me, in all honesty, for me personally, I do one thing at a time. I'm a one track mind kind of guy. It's like I got to do this task, I have to do this task. I'm a pretty poor multitasker compared to other people. Very, very poor. So, hey Dylan, thank you. I really appreciate that. How you been, Dylan? And you're up really late. All right. Very good. Okay. Well, well, I want to thank you guys for coming on out here to the stream today. I know today was pretty heavy with some material. Doing well, correct? Yeah, you are pretty up pretty late, I ain't gonna lie. You caught me at the tail end here, but you know what? I always appreciate you, my dude. I want to thank everybody for coming out here to stream. Thank you so very much. You guys are absolute legends. Absolutely wonderful. Thank you so much for putting up with me. I know today was rather heavy, but we're going to do a couple more examples here from this section tomorrow to start off with so we can wrap up chapter 3. Look up at a couple more different variations, and we'll get that going, okay? All right. All right, everybody. We'll see you tomorrow. Same time, same place. Again, if you have questions, you guys know where to find me. All right? Thanks, Dylan. Appreciate you. Emma, if you get a chance to contact me on Discord, please do so. All right. Otherwise, just contact me via email and we can talk about some of the problems that you had there. All right. So, you can go ahead and do that. All right, everybody. Have yourself a wonderful night. And remember, as always, stay safe, stay healthy, but most importantly, stay sane. All right? Have yourself a wonderful night, everybody. Take care of yourselves. See you later. Bye. Bye, everybody.